Hello and welcome to lesson 4.4. We're talking about are you rational, right? So, are you rational? What does rational even mean, right? So, let's dive into our ready, set, go. So, find the roots and domain for each function, okay? So, remember the roots, we've talked about roots a lot, but the roots is when the function or your x-intercepts, right? X-intercepts. That happens when y is equal to 0. So we can think about this as f of x is equal to 0. And we know that for that to be true, all of these should be equal to 0. So then I get that my roots is that x plus 5 is equal to 0. X is equal to negative 5. X minus 2 equals to 0. X is equal to 2 here. X minus 7 is equal to 0, and I got that x is equal to 7. All right, so these are my roots, and what is my domain, right? So without even thinking about it too much, what you need to realize is that this is like a function, right? These are just a function, and you can plug in any value you want. It can be 0.001, it can be 200,000 million, whatever number you want it to be. And it's always going to be able to have an actual y value. Okay, so as a result of that, my domain here is just negative infinity to infinity. You can write it as x is equal to all real numbers. Okay, same concept. For g of x, right? So we have that. Two ways of doing that. You can use your quadratic formula. I don't really like quadratic formula in this particular case um, because quadratic formula, simply because you can factor this out. So g of x is equal to, we're going to go ahead and expand this out. So this becomes x, sorry, not expand it, I mean factor it, x, and then thinking about numbers that multiply to 6 and add up to 7. So it's plus 1 plus 6, right? Again, we want g of x is equal to 0. So then that means that x plus 1 equals 0, x plus 6 equals 0. So then I'm left with my roots. I'm left with x is equal to negative 1, and then x is equal to negative 6. Okay, these are my roots. Okay, I can label these x1, x2, x3, x1, x2, and same concept here. My domain is going to simply be negative infinity to infinity, or all real numbers. X is equal to all real numbers, right? We know that because I can plug in again any number that I want and it will be defined. Okay, let's think about k of x. So I want to find the roots, and I don't know if you've noticed, but this and this are very similar, right? Okay, but I want for k of x, my roots, let me use a different color here. So I want my roots, again, I want k of x equals to 0. So when is that going to happen? Right? Like when will k of x equal 0? Means that when this has to be 0. But what is that one of those commandments? Is that I cannot divide by what? By 0, right? So here it's a special case because there is no roots. Okay? There is no roots, there are no roots. There are no roots. Okay? Um, and now what about my domain? So I know that my domain, when I have a rational, when I have a something like this is a rational function, right? I cannot divide by 0. Cannot divide by 0. Those will be undefined. So then I know that my domain here is all real numbers except what? So it's x is equal to all real numbers, except x cannot equal your roots, right? -5, 2, and 7. So I cannot have a -5 here. If I plug in a -5 for them, this will be 0. Because then I'm going to be left with, let's think about this. This k of 5 is equal to 1 over 0, which is not defined. This is an undefined, right? We cannot divide by 0. So therefore, my domain is this. Except x cannot equal -5, 2, and 7. You can write this, I mean, I'm not going to say you can write this a different way if I were to ask you that. -infinity up to -5, union -5 to 2, parentheses again, union to 7, union 7 to infinity, right? I'm not really going to talk to you about this. I think this is the, well, simplest and easiest way to think about that. Yeah, let's think about h of x. So again, I want h of x equals to 0. So I can essentially, I'm going to kind of set this equal to 0. So I'm left with 1 over x squared plus 7x plus 6 equals 0. I'm going to solve for x. Let's just say that. So 1 is equals to 0 is not a true statement, right? So this can never be actually be true. So there are also no roots. There are no roots here. No roots. And what is my domain? So my domain will be x is equal to all real numbers except when? When this is equal to, when that is equal to 0, right? So we kind of found that from part 2, question 2. Except x cannot be equal to -1 and -6. So we tend to write them as, well, it doesn't matter, -6. Okay. You can also write this as -infinity up to -6 union -6 to -1 union -1 to infinity, right? These are totally valid ways, but this is kind of how you would write it. It's just a lot more simple, right? And again, there are no roots, no roots here. Okay. Do the roots of the polynomials in problems 1 and 2, right, tell you anything about the graph of the reciprocal? These are the reciprocals. So reciprocals were 3 and 4 of the polynomial presented in k of x and h of x. Explain. So the roots told us what? What do the roots tell us? Okay, so I hope you're able to realize that the roots of f of x and g of x tell us where the rest tells us where k of x and h of x respectively are undefined, right? Are undefined because we would divide by 0. Because we would be dividing by 0. Okay, so I think that's important that they were the reciprocals of them, and it tells us where it's equal to 0, so therefore you cannot divide by 0, right? Okay. The y-intercepts of the polynomials in problems 1 and 2 tell you anything about the y-intercepts of the functions in problems 3 and 4. So where were the y-intercepts? So my y-intercepts, my y-intercept was when x is equal to 0, right? So for f of 0 was equal to 5 times -2 times -7. So f of 0 was a -70, +70, +70. Okay. And then for, what was it for k of x? So k of 0 was equal to, let's just do that, is equal to 1 over 70, right? So what did you automatically pick up? I mean, let's do the other one, but something there should be a little bit clear. Let's do for g of x. So g of 0 is equal to 6, right? So then h of 0 is equal to 1 over 6. So what can you tell? What happened there? Okay, so the y-intercepts of k of x and g of x are the reciprocals, right? Like it's just the reciprocals of the y-intercepts of f of x and g of x, of f of x and g of x respectively. Okay, so that's like a really interesting concept. Which is nice to know, right? This is kind of what our thoughts should kind of be. Okay, rational functions are needed because polynomial functions are not closed under division. A rational function is defined as a ratio of two polynomial functions, okay? Or f of x equals to p of x over q of x, where q of x is not equal to 0. Again, right? We know the values of x that make q of x equal 0 are not in the domain. Is it possible for f of x to equal 0? So let's kind of just think about this. Can f of x, so if f of x is p of x over q of x equal to 0, that means that p of x is equal to 0. So yeah, right? So f of x can equal 0 if p of x equals 0, as long as q of x does not equal 0. Okay, cool. Let's think about our set. So for each function, identify the degree of the numerator and the denominator. Okay, so how are we going to do that? So again, this is a power of 1, 1, and 1. So my degree there is 3, right? So you add them up. So my numerator is equal, degree of numerator is equal to 3 all over my degree of my denominator is equal to 1, 1. This is just equal to 2. Okay. Let's here we have a 1 and a 1. So my degree of numerator is equal to simply 2. And then my degree of my denominator, this is 1, this is a 1, also equal to 2. Okay. And then here we have 1 and 1. So my degree of my numerator is equal to 2. And then my degree of my denominator is equal to, there's a 1 here, and a 2 here, right? There's a 2, so we take 2. So 2, 3, 4. Times a little bit different. My degree there is 4. So which functions in problems 8 to 10 has a horizontal asymptote at y equals 0? Okay, so remember that a horizontal asymptote or asymptote happens when the degree of the numerator is less than the degree of the denominator. Okay, so right off the bat, the one that has a degree numerator that is less than is right here, right? So that would be problem number 10, h of x. Okay, so that's the function. Cool. Write the equation of the vertical asymptotes of the following functions, indicative of the graph if the function has a hole in it instead of a vertical asymptote. Okay, so let's kind of talk about this. So 12 has really ugly numbers. We're not gonna freak out. My first instinct is to always try to see if I can factor this out. And I can, right? So 3x is here and then 3x. And where did I get that? Because I just think that that's going to work for us. And also, you have to be kind of a little bit intentional with what you're doing. So I'm hoping that something will cancel out with this. I'm not entirely sure. Maybe, who knows? And then the bottom, I'm also going to be able to factor that. So I need to think about numbers that multiply to 25 and give me plus 30. So I would say this is going to be a plus and a plus. And I want a 5 and a 5. And let's just check that out to see. This is 3x squared plus 15x plus 15x, that's 30x, so bingo. And then the bottom, I can factor out an x, and I'm left with 3x plus 5, okay? So let's think about this. So where is there going to be a vertical asymptote? So we can see that I can cancel one of these out, right? So that tells me that if I can cancel one of those out, that means there's going to be a hole. So there's going to be a hole at 3x plus 5 equals 0, right? So then I'm going to solve for x. So this is 3x is equal to negative 5. So x is equal to negative 5 thirds. So there's a hole at x equals negative 5 thirds. And then where's my vertical asymptote? So if this simplifies down to 3x plus 5 over x, so my vertical asymptote, VA for short, happens at x is equal to 0. Okay? And I have a hole at negative 5 over 3, negative 5 thirds. Okay? It's important. What about 13? So 13 looks a little bit nicer for us. Again, my first instinct is to always factor, right? Like if we're in this section about rational functions, you should always try to see things as in factored form, not standard form, right? That's kind of like what I want you to think about and what I want you to get at. So the first, this is x. I want numbers that multiply to negative 8 and add up to 2. So I'm going to think about like, off the top of my head, I can think about 4 and 2, right? So if I have a positive 4 and a negative 2. So plus 4 minus 2. And does that work out for us? We have x squared minus 2x plus 4x. Yes, that's going to be 2x minus 8. In the bottom, can factor. This is a difference of squares. So this becomes x minus 4, x plus 4. Okay, so we do have a hole, right? So this is going to go away, go away. So we have a hole whenever x plus 4 equals 0. So then x is equal to negative 4 is my hole right there. And then my vertical asymptote, this is equal to x minus 2, x minus 4. The vertical asymptote happens when x minus 4 is equal to 0, so x is equal to 4. Okay, so this is a hole. Let's use a different highlighter. This here, vertical asymptote, hole here, and vertical asymptote there. Okay. Okay, 14 looks interesting. Let's do it. I can see that the top is also considered to be a difference of squares, if I'm not mistaken. So we see that this can be thought about as 6x minus 7, 6x plus 7. Let me just make sure that that's accurate. So we get 36x squared. The plus 7 times 6 is going to cancel out. Yep, so that's totally fine. Minus 49. And then in the bottom, what do I have? So the bottom, I can do x, and I'm going to have a -7, -7. Okay, so can I cancel out anything? No, so there is no holes. So there are no holes. Let's just say there are no holes. And then my vertical asymptotes happen when vertical asymptotes happen when x -7 equals 0. So I got that x is equal to 7. So this is my vertical asymptote. And there are no holes. Okay, good. Nice. Use long division to rewrite the rational function as in an equivalent form that reveals the slant asymptote. So not going to get too much into it, but again, a slant asymptote happens whenever there is a when the degree of the numerator is exactly more, right? So a slant asymptote is when the degree of numerator is exactly one more than denominator. I think that's an important concept that um, we kind of need to think about, okay? Because that only happens when there is a degree, 1 degree more, okay? If not, there's no slant asymptote, okay? So for example, here, my degree here is 2, degree here is 1, so that should work, okay? Now, how am I going to do this? It tells us we're going to do a long division, right? So long division with the fraction house. Let's use a different color. So I'm going to get, let's use a different page for this just so I can, let's add a page. Okay, perfect. Let's do it. So I have x minus 1 into 2x squared plus 3x plus 4. Now you have to ask yourself, how many times does x go into 2x squared, right? So that's going to be 2x, right? Because x times 2x is 2x squared. And then you multiply this here to both of them, so you got 2x squared. This is very similar to division with the house, right? We've done this in the past, well, regular division. And then 2x times -1 is minus 2x. And here we subtract them. So they go away, we get 0. 3 minus -2, -5x, and then we bring down this 4. So plus 4. How many times does x go into -5x? That's going to be minus 5. So we get -5 times x is minus 5x. -5 times -1 is plus 5. Here we go. We're going to subtract them. So -5 plus 5, it's 0. And then 4 minus 5 is going to be negative. Oh, something happened. 2x plus 4. 2x squared. 2x times -1 minus 2x, subtracting these out. Oh, this should have been a plus. Sorry, this was a plus. This was a plus 5x. So then, okay, so let me reiterate. This should have been a 5x, right? And then x plus 5 here. And then we get that this is 5x minus 5. Subtract them. 4 minus -5, it's plus 9. So this is a plus 9, and we write it over my denominator. My denominator is x minus 1. Okay, so this is my equivalent form, and my slant asymptote is only going to be, what are they asking for? This is my equivalent form. So let's just say f of x is equal to 2x plus 5 plus 9 over x minus 1. and my slant asymptote is y is equal to 2x plus 5. Okay. Let's see how this looks in a graph. So where's my calculate for? So calculate for. Okay, so I'm just gonna do this for the fun of it. So 2x squared plus 3x plus 4, dividing that over x. Let's just put parentheses to be on the safe side. X minus 1. Okay, so let's graph that. Oh, interesting. Look at that. Beautiful. And then let's grab our equivalent function that we just found, the equivalent, right? So it's 2x plus 5 plus 9 over. This is important when you put parentheses, x minus 1, close them up. And let's graph those. So that's the red one, right? So beautiful. And then let's, oh, where did that go? Oh, right here. What's going on? Okay. And then my slant asymptote, let's graph the function 2x plus 5. So there you go, right? So my slant asymptote is exactly 2x plus 5. So we see that it's, the bounds, what is happening? That's never happened before. So if we were to keep on going forever and ever, let me change my window to negative. Interesting, that's so bad. Okay, well, let's just, right, you'll see that it's just gonna touch it slightly, right? That's what a slant asymptote is. Cool. Let's do 16. 16. Okay, cool. So then we're gonna get x minus 4 on the outside of the house. Inside we have x squared minus 3x minus 5. This would be an x. Multiply them out, you get x squared, x minus 4 times negative 4 is minus 4x. We subtract them, so 0. Negative 3 plus 4 is x minus 5. Here we have that x goes into x just plus 1 time. This is x. This is negative 4. And we subtract them, so we get 0. Then we get negative 1. Negative 1. So then we write this as minus 1 over x minus 4. Okay, so then g of x is equal to x plus 1 minus 1 over x minus 4, and my slant asymptote is y is equal to x plus 1. Perfect, and then let's finish it off with 17. Let's see. So, okay, great. Let's do it. So I get x squared minus 4x plus 4 into this big division house, x cubed minus 3x squared plus 5x minus 1. So how many times does x squared go into x cubed? Just going to be x. We have x, and then we multiply it out, so we get x cubed minus 4x squared plus 4x. And here we subtract them, so this is 0. Negative 3 minus negative 4, this becomes a positive x squared, and then 5 minus 4 is plus x. Bring down this negative 1 minus 1. X squared goes into x squared exactly 1 time, and then now we're left with x squared minus 4x plus 4. We subtract them here, we get 0. It's happening 0. Then we get 1x minus negative 4, so we're adding them, so we get 5x. And then negative 1 minus 4 is going to be negative 1 minus 4, so negative 5 minus 5, right? So then we write this up as plus 5x minus 5. This is technically my remainder over x squared minus 4x 4. So then again, h of x is equal, I don't know why I haven't been doing this earlier. Copy, paste, right? And then my slant asymptote is only equal to y is equal to x plus 1. Okay, great. So we've done those. Okay, cool. Let's talk about 18. So this is the go section. Okay, so take the domain of the following rational functions, right? Write the equation of the vertical asymptote and sketch in the vertical asymptote on the graph. Put an open circle in the graph anywhere it's undefined. So again, I think that probably means holes, where there's any holes, right? Okay. So again, my domain here is x is equal to all real numbers, except, right? Except when x cannot, except when, well, not except when, but just except x cannot equal to 2 and negative 5. Okay, I hope you see that that's because of this, right? So vertical so we can simplify this to 1 over x plus 5. So we know that there's going to be a hole at x minus 2 equals 0. So then x is equal to 2. And there's a vertical asymptote at x when x plus 5 is equal to 0. So x is equal to negative 5. Okay, so then on our function, we know that there's a 2, there's a hole there, and then right here, negative 5, it's a vertical asymptote. Okay, perfect. What about 19? Again, so my domain for these from the graph, you can tell that it's x is equal to all real numbers, except x cannot equal negative 6 comma 4, right? So vertical asymptote, so this is equal to 1 over x minus 4. So my vertical asymptote happens when x is equal to 4. Right, so we see it right here, vertical asymptote right there, and there's a hole at negative 6. So negative 6 is over there. Okay, perfect. Okay, so now we have that this is going to be equal to, this goes away there, this goes away there, left 1 over x minus 3. So my domain, again, x is equal to all real numbers, except x cannot equal to negative 10, 3, or 7. Okay, so again, it just follows from the fact that there's holes there, right? So if there's a hole, it cannot be part of your domain. And then we have our vertical asymptote at x is equal to 3. Okay. Okay, so it's vertical asymptote. So let's sketch it right here, and then we have to circle our where it's undefined at negative 10, which is not even on there, and then at 3, which is the thing, and then at 7, 5, 6, 7. So right there. Let's do it there. Okay. Perfect. This wasn't terrible. I hope that made sense. Please again reach out if you have any questions, comments, or concerns. Go to office hours and continue having a great day.